from the Department of Chemical Engineering. This is a group presentation by Group 26 on induced draft cooling towers and its application to the first law of thermodynamics. So in this presentation, we are going to talk about this equipment used in most of the process industries in Ghana and worldwide, which is the induced draft cooling towers and how it is applicable to the first law of thermodynamics. So the overview of cooling towers. Most industrial production processes need cooling water to operate efficiently and safely. So the refineries, steel mills, petrochemical manufacturing plants, electric utilities, and paper mills all rely heavily on equipment or processes that require efficient temperature control. So these process industries such as the refineries, steel mills, and these petrochemical manufacturing plants operate with very big machines, and they need an equipment that is going to efficiently control their temperatures, the temperatures of these machines that they use, so that these machines don't overheat. So they resort to the use of these cooling towers to be able to efficiently control the temperature of these machines to prevent them from overheating. So the cooling water system control these temperatures by transferring heat from hot process fluids into cooling water. How this happens, the cooling water itself gets hot. Before it can be used again, it must be either cooled or replaced by a fresh supply of water. The cooling tower is a heat rejection device that extracts waste heat to the atmosphere by cooling a stream of hot water. This type of heat rejection is termed evaporative because it allows a small portion of water being cooled to evaporate into a moving airstream and thereby provides significant cooling to the rest of that water stream. The heat that is transferred from the water stream to the air stream raises the air's temperature and its relative humidity to 100%, and this air is discharged to the atmosphere. So the specific type of cooling tower in this presentation that I'm going to talk about is the induced gas cooling tower and its processes and how the first law is applicable to it. So the induced gas cooling towers. The induced draft cooling tower is also known as the induced draft mechanical draft tower. So in other books you can find either the induced draft cooling tower or you can find the induced draft mechanical draft tower with mechanical draft emphasizing the use of a fan which is powered mechanically to induce the airflow through the tower. So this type of cooling tower, they have their fans at the top, and these fans are powered mechanically, and these fans also induce the airflow through the tower. So these fans at the top of these towers, they are the ones that induce the airflow through the tower, so they pull the airflow through the tower outside to the atmosphere. So an induced draft mechanical draft tower is a draw-through arrangement where a fan located at the discharge end pulls air through the tower. So like I said, the fans at the top of this towers, they are the one pulling the air through the tower. So they are pulling the air to the end, to the discharge end, which is the top, through the tower. The fan induces hot moist air out the discharge. So this produces low entering and high exiting air velocities, inducing the possibility of recirculation in which discharge air flows back into the air intake. So by inducing the hot air or the hot moist air out into the atmosphere, it prevents air from flowing back, which is the recirculation of air back into the tower. So the air exiting these fans, so the air exiting into the atmosphere exits at very high air velocities and prevents low entering air velocity. So air with low velocity cannot recirculate back into the tower, but only high exiting air velocities are able to leave the tower by the use of these fans. have types of induced draft cooling towers. So the induced draft cooling towers are characterized as cross-flow and counter-flow designs by virtue of air-to-water flow arrangement. So the difference lies in the fill arrangement. So we have the fill arrangement over here. So this is the fill arrangement. So that is what differentiates between the cross flow and the counter flow induced draft cooling tower. So let's talk about the counter flow cooling towers. In the counter flow, induced draft cooling tower, air travels vertically across the fill sheet opposite to the downward motion of the water. So in this counter flow cooling tower, the air travels vertically downwards. So you can see the air traveling vertically downwards opposite to the downward motion of the water. So you can see in the downward motion of the water as the air is traveling vertically downwards, air enters an open area beneath the fill media. So the air entering this open, the air is entering open beneath the fill media. So this is the fill media and air is entering beneath it and is then drawn up vertically. So as the air enters, it is drawn up vertically. So this we have this the air entering this small opening beneath the fill media and it is going to be drawn up vertically. The water is sprayed through pressurized nozzles and flows downward through the fill media opposite to the airflow. So the water is then going to be sprayed downward through the fill media opposite to the airflow. So as the airflow enters through the small opening beneath the fill media and is drawn vertically upwards, the water is sprayed through pressurized nozzles and flows downward through the fill media. So the flow of the water and the flow of the air are opposite to each other. So the flow of the water is opposite to the airflow. So let's move on to the next type of the induced draft cooling tower. So let's talk about cross flow cooling towers. And in cross flow induced draft cooling towers, air enters one or more vertical faces of the cooling tower and moves horizontally through the fill material. So we have the fill materials over here. We have one on the left and one on the right. So we have dry air moving through the opening over here horizontally. We also have the dry air from this side moving horizontally through it. So water draws by gravity. So the water draws by gravity and the air passes through the water flow into an open plenum area. So this is the open plenum area. A shallow pan type elevated basin is used to distribute hot water over the tower by fill means of orifices in the basin floor. So this is the distribution basin. This is going to distribute water. This is going to distribute the hot water over the tower. It has small holes in it called the orifice in the basin floor. So the application obviates the need for a pressure spray distribution system and relies on gravity distribution. So more on cross-flow cooling towers. Cross-flow towers are also sub-classified by the number of fill banks and air inlets that are served by each fan. The tower indicated in the schematic above is a double flow tower because the fan is inducing air through two inlets and across two banks of fill. The surface enclosing the top structure of an induced draft cooling tower, exclusive of the distribution basins on a cross-flow tower, is called the fan deck. So the fan deck is always at the top of a cross-flow cooling tower, which is exclusive for the distribution of basins. Yes. So the mode of operation of induced draft cooling towers. So hot water enters the tower and is distributed across the fill media Air is drawn into the tower by a mechanical fan, inducing a flow of air through the system. Heat exchange occurs and part of the water evaporates, lowering the temperature of the water. So the cooled air is then collected at the bottom and sent back to the system for reuse. So when the hot water is condensed back, water, the condensed water is not discarded but rather taken back into the system for reuse. And this conserves the use of water by these process industries. So the exit air, now warmer and containing evaporated water, leaves the tower, possibly passing through the drift eliminators to reduce water loss. So moving on to the process flow diagram for induced gas cooling tower. So for this, we have the hot water from the process entering the distribution basin, which is being sprayed downwards through the fill medium, and we have the air being drawn in from beneath. We have air in from beneath, which is moving vertically opposite to the water that is being sprayed across the fill medium. So this water is going to be condensed and collected at the bottom, and the cold water is going to be sent back into the system for reuse. And we have the rejected heat or the exit air moving at high velocities into the atmosphere. And when we look at this is how the whole thing is going about. So we have the air in the blue arrows, and we have the water, the hot water from the process across the distribution basin and sprayed downwards. And you have the exit air at the top with the fan rotating here. And you have the condensed water being collected at the bottom and sent back into the system for reuse. The application to the first law of thermodynamics. And we know the first law of thermodynamics is applicable to both open and closed systems. So moving on, we are going to see whether this equipment is working on either open or closed system, and we are going to look at some of the equations that are going to back this operation of this equipment based on the first law of thermodynamics. So an induced gas cooling tower works by cooling water through evaporation. So the process involves heat transfer between water and air, and the first law of thermodynamics is crucial in understanding the energy exchange that takes place in the system. The first law of thermodynamics governs the energy transfer in an induced gas cooling tower. The energy balance equations reflect the sensible heat lost by the water, the latent heat carried away by the evaporated water, and the heat transferred to the air. The cooling tower works by evaporating a small portion of water, thereby reducing the temperature of the remaining water while transferring the heat to the surrounding air. So, for the first law of thermodynamics, we know that the first law states that energy cannot be created nor destroyed, but can only be transformed from one form to another. In its simplest form for a control volume, it is expressed as the change in U equals the change in Q plus the W, which is the work done, where change in Q equals the heat added or removed from the system. So this accounts for the heat from the hot water into the system, and then heat from the warm air which is exiting the system. So the heat change over there, that is what this change in Q is accounting for. And the W is equal to the work done, but for cooling towers the work done is zero, since the only energy transfer is heat. There is no mechanical shaft work or anything over there. There is only change in heat, change the heat from the water and the heat from the warm air exiting the system. And you have the change in U, which is the change in internal energy of the system. In the case of a cooling tower, the energy balance involves heat transfer by sensible heat. The temperature change, so the heat transfer by sensible heat is the temperature change of the water and air, and the latent heat, which is the energy required for the water to evaporate. So Energy balance in a cooling tower. So for a cooling tower, we have two energy balances, one from the water side and one from the for the air side. Sorry. So we have the one from the water side called the water side energy balance and the air side energy balance. So for the water side, we have the MW, which is the mass flow rate of water, minus the enthalpy of water in, minus the enthalpy of water out, minus the W evaporate times. So this accounts for the latent heat lost by the water. So the latent heat lost by the evaporating water is accounted by this, plus the mass flow rate of air, sorry, then the enthalpy of air leaving and and minus the enthalpy of air entering. So we have MW minus MW bracket open H in minus H out equals W evaporate times HFG plus MA bracket open HA out minus HA in, where MW and MA equals the mass flow rate of water and air respectively. H in and out equals the enthalpies of water entering and leaving the tower. So and HA out and HA in, enthalpies of air entering and leaving the tower as well. And W evaporate times the HFG, which is the latent heat lost by the evaporating water. And for the air side, we have MA bracket open HA out minus HA in equals W evaporate times the HFG plus MW bracket open H in minus H out, where MW again and MA are mass flow rate of water and air respectively. H in and out, enthalpies of water entering and leaving the tower, HA out and HA in, enthalpies of air entering and leaving the tower, and WL times HFG, latent heat absorbed by the air from the evaporating water. So moving on, we are going to talk about the overall energy balance or the overall equation for this energy balance in a cooling. So the general form of the equation, so the overall equation is this. So MW bracket open H in minus H out plus MA HA out minus HA in is equal to W evaporate plus A times HFG. So this is working for an open system. That's how we have the equation on this equation. But for assuming this was a closed system, the equation which was changing U equals changing Q plus W was going to be used. But for open system, this is the type of equation we are going to use, taking into account the mass flow rate and the enthalpies moving in and out, where MW times H in minus H out equals the sensible heat lost by the water. So this is accounting for the sensible heat lost by water, and MA HA out minus HA in equals sensible heat gained by air. So this is the sensible heat gained by air is equal to the W evaporate times the HFG, which is equal to the latent heat transferred to the air due to the evaporation of water. Yeah. So this equation represents the total energy balance in the induced draft cooling tower. The heat lost by the water, both sensible and latent, is equal to the heat gained by air. So this sensible heat lost by the water is equal to the latent heat gained by air. So the heat lost by the water, both sensible and latent, is equal to the heat gained by the air. So this is equal to this. So this one being lost is equal to this one being gained. So the heat loss is equal to the heat gained. So the heat lost by the water is equal to the heat gained by the air. So this equation can now be used to analyze the cooling performance of the tower, taking into account both the heat lost by the water and the heat gained by the air. So let's talk about the advantages of the induced draft cooling tower. So the first one is recirculation tendency is less a problem. So there is no air from the atmosphere entering back into the tower since the fan at the top over there is drawing air at high velocities, and the atmospheric air is at a very lower velocity. Hence, the high velocity air from the tower is going to be drawn out, preventing the low velocity air outside the tower being to be drawn in. So the air that is thrown out from the top of the cooling tower has no chance of getting back into the cooling tower. So the push of the fan adds to the upward thrust of the warm air. So yes, so the fan pushes the high velocity air, and so it pushes it, adding an upward thrust to it. So it adds an extra force to it, preventing the air from falling back or the air from getting back into the tower again. So the induced rate can be square as well as round. The distribution system is that of a sprinkler, which is considered to be the most efficient water distribution system. So noise level is very low because the fan and the motor are placed on the top of the cooling tower. So we know that for this individual cooling tower, we have the fan at the top. So when it's in operation, the noise that is going to be produced is going to be very low since it is at a very high altitude. So to the observer, he's not going to come into contact with so much noise from the fan and the motor since they are placed at the top. So they are not in level with the observer. Yes, so the noise level for the observer is going to be low. A forced draft cooling tower cannot be a cross-flow type model. An induced draft can be either cross-flow or counter-flow. So to my references, okay, we have the link to the book which contains all the necessary information about this induced draft cooling towers, and also we have the model predictive control of induced draft cooling towers in a large scale cooling plant. Yes. So these are the two solid references for this project.